Hi everybody, this is Miss S from Excelsior Charter School, and today we're going to be going over geometry lessons 1-1 and 1-2. So to begin with, we're going to go over some vocabulary today: inductive reasoning, conjectures and counterexamples, isometric, orthographic, foundational drawings, and nets. So let's jump right in. You've probably heard of deductive reasoning before, and I know that you have used it before. Anytime you do scientific method or something like that, you're using deductive reasoning. So deductive reasoning usually goes from a general statement, and then it brings it down to something very specific. And you can make sure when you're using deductive reasoning that the conclusions are correct if all the statements that you say are correct. Inductive reasoning is the opposite of that. Inductive reasoning starts with something really specific and then draws a general conclusion. And you can't be 100% certain that it's always accurate, but in your life you can utilize it as one way of thinking about a subject. Here are some examples. We'll go with the pink first, deductive reasoning. So the statement is that all students in this class play guitar. And Sam is a student of the class. Therefore, Sam must play the guitar. That's a true statement. Example number 2 here. At the conference, all the people present are 30 or older. Maria is in the room. Therefore, Maria is at least 30. So that's deductive reasoning. It's very organized. It's very scientific in the way it goes from one step logically to the next. So inductive reasoning kind of works backwards again. So, for example, every quiz has been easy, therefore the test will be easy. Now, that is an assumption that you can make, but there's no way to guarantee that that is going to be true. That test could be really hard. So the same thing here for number 2. The teacher used PowerPoint in the last few classes, therefore the teacher will use PowerPoint tomorrow. Also true, but maybe they decide to use something different. So it is a logical way of thinking through things. It tends to be used with patterns a lot. So for example, let's use, I love sports and I'm the athletic director at Excelsior. So let's say something like this. If you play basketball on Monday, and then you play basketball on Tuesday, and then you play basketball on Wednesday, it would be logical for us to assume that if you're going to play something on Thursday, you would play basketball. However, that might not be true. Maybe you decide to play a different game. Maybe you decide to rest. There's no way to know for sure that you would play basketball on Thursday, but it is a relatively safe assumption, and that's what inductive reasoning is all about. So now to move on to our next vocabulary word, conjecture. That is the conclusion that we came to as a result of that inductive reasoning. So our idea that you were going to play basketball on Thursday is a conjecture. We suspect that to be true due to the evidence that we already have, but we don't have any proof as of yet. So now we move on to counterexamples. Imagine for a second that you are in a classroom full of students and a teacher. And imagine the teacher says something along the lines of this. Here's their statement. All students in this room have brown eyes. Do you think that statement would be true or false? So it is either one or the other, because that's an all-in statement. Everyone has brown eyes. So the likelihood is that that statement is false. Not everyone in the room would have brown eyes. But the question is, what is a counterexample? So a counterexample would be anyone in that room who doesn't have brown eyes. An example would be someone who has brown eyes, but a counterexample is someone who doesn't have brown eyes. So anyone with blue, green, hazel, any other color other than brown would be a counterexample to that statement. Now, a good question here is, how many counterexamples do you need in order to prove a statement false? And the answer to that is just one. If you have just one counterexample that can prove the statement false, the statement is inherently false. And that's how you use counterexamples. Okay, so we move on to the 3 different kinds of drawings we're going to cover from lesson 1-2. So an isometric drawing is the first one. And when you were a little kid, if someone was to ask you to draw a picture of a house, you may draw something like this. And that would have been just fine as a child. However, as you grow and as you age and mature, you learn different things about the way that you react with the world. And one of the things that you learn is that this drawing is a two-dimensional drawing, and we live in a three-dimensional world. So an isometric drawing is one way to draw in 3 dimensions. So this is isometric dot paper, and I just found it online. I Googled it, and you can pull down the image of the paper, and you could download it to your iPad and use it for your own stuff, or print it however you wanted to do it. So now let's say I wanted to draw a house again. Let's see how this might go in 3 dimensions. That same house might look something like this now, and you can see that it has a front and it has a side. So you could add doors and windows and whatnots if you wanted to, but now at least you see it's in a 3-dimensional symmetry. In geometry, we use 3 dimensions quite a lot. However, we don't often use the isometric dot paper. So just something to be thinking about. Now we move to orthographic drawings, and what orthographic drawings do is they take those 3-dimensional drawings like you could have made on an isometric dot paper, and they show it in 2-dimensional ways, from the top, from the front, from the side, just like in this graphic here. And orthographic drawings are frequently used by engineers and designers and architects and technical artists so that they can see what the specifics of the product that they're trying to create. Here in geometry, however, we very rarely use orthographic drawings. So now on to a foundation drawing, which shows the base of a structure and the height of each part. So this image that I have here is of the Willis Tower, which is in Chicago. I love to travel. I've been here several times, and the observation deck is on the 103rd floor. It's actually 1,353 feet in the air, and they have a new part called the ledge, which actually sticks out in clear kind of plexiglass, and you can step out over the ground that high up on just some clear plexiglass, which is a little scary, but it was also a lot of fun. So when you're doing construction and engineering and architecture and things like that, sometimes a foundation drawing is what's easiest to notice about the structure. So let me show you what a foundation drawing of the Willis Tower would look like. So here is the square base of the Willis Tower, and each of the numbers represent how many floors there are in each of those 9 sections. Obviously, this is a fairly crude drawing as I just drew it here, but that's how a foundation drawing works. Again, here in geometry, we will rarely use these, but all of these drawings are good ways to kind of get a representation of how objects look in space and different ways that we can represent those things. So our last one here, a net, is something that we will use frequently in geometry. It's a 2-dimensional pattern that you would fold up to form a 3-dimensional figure. So let me give you an example. So right here on the top left, we have a rectangular prism, and notice how each of the pieces correspond with the different colors. And so this net is right here, and if you were to fold it all up, you would have this figure over there. And the same holds true with the pyramid. If you were to fold all those pieces up, you'd get the pyramid. The cylinder always looks a little bit funny because, believe it or not, if you were to open up a cylinder and roll it all out, it actually becomes a rectangle, and just the top and the bottom are the circles. And then a cone, same kind of thing. If you were to open up a cone, like an ice cream cone, and lay it all out, you would have this blue shape right there. And then you have the top of the cone, of course, is the circle. And so that's how you use nets. So that's the end of how to do this lesson, you guys. Good luck, everybody. I hope you guys do great.